In this video, we're going to discuss the weirder looking asymptotic bound of n log n, or big O n log n, since this is an upper bound. Where we see this often is in our sorting algorithms, like quicksort and merge sort. I actually made a video a while back. I don't know if it's the best explanation, but comparison sorting algorithms, where we don't know any special property about the array, have a lower bound of n log n. And I did a video on this. I don't know how rigorous or good of a proof it is. It's something I just got from class. But it's good to see exactly why this bound manifests. And if you want to see the exact math, go to the quicksort video I've done, go to the merge sort video. Those will help you deeply understand what's happening. But I just want to give an introduction to this bound, and we're going to implement merge sort. We'll implement merge sort together, and I want to walk you through the thought process of when we're writing this code out and what we're thinking as we're doing it. Another place that we see n log n is when we are building a heap. If I have an array of n items and I want to build a heap that holds n items, that n log n, for each of the n items in the array, we're going to insert into a heap that might have n items. And we're going to go down at maximum an upper bound of log n levels when we bubble down or bubble up. That's where n log n can manifest as well when we're dealing with heaps. We're building a heap. This is not to be confused with the build heap phase in heap sort. It's different when you're building a heap from scratch and you are inserting items like that. So this is a bit complicated. So again, reference the heap sort video, merge sort, quick sort videos for the exact math behind this. But what I want to do right now is I want to implement merge sort with you, and I want to look at the recurrence with you so that we can understand in depth what is happening. Imagine that your interviewer asks you, implement merge sort. So let's implement that right now. We're dealing with linked lists here. What we're going to get as an input is a node. So let's establish that right now. What we see here is that we get a node, and we're passed in the node as, we just call it head. This is a reference. We grabbed a reference to a single node, and it's a linked list of items. The item is linked objects in memory. They're linked by memory address references. So in reality, they're all independent objects. It's just that they have an understanding about each other, and this causes them to be a conceptual structure, and it becomes a linked list. So what we want to realize is whenever we look at the parameters to a call that's going to be recursive, we want to understand how we're going to deal with the different states that can happen. So I want you to imagine this. If we get a single item or we get nothing, what does that mean? What would I return from a function that's going to sort a linked list if the linked list has one item or no items? If it has no items or a single item, then we're just going to return the item. The reason we return just the item is a single item sorted. Empty list is sorted, it just has nothing. That is the base case. The base case is the obvious answer. We're going to see this later when we deal with dynamic programming, when we deal with recursion, when we deal with backtracking. When we're crafting these recursive functions, we're always going to see what is the obvious answer. The obvious answer is going to be the base case. Instantly I know the answer. What we do is we say if head equals null, or if the next is null, then I return the item itself. If the item is null, it's just null. If the next is null, it's a single item list. So let's write that out. So if you are ever stuck in an interview and crafting a recursive function, always know what is obvious to me, what is immediately apparent, and what will allow me to know this is what I return from this function. I know the answer. This input state signifies something instantly apparent about what I need to return. So that's how we craft our base cases often for recursive functions. And what we need to do is we need to cut the linked list in half. The linked list is a connection of multiple memory addresses held together. And we need to chop that in half because merge sort works by chopping the input in half, recurse, chop it in half, recurse, base case come up, base case come up, and then we put it back together, and that's how the recursion pans out. We need to cut the list in half, and we can create an abstraction to do so. So let's create a mid reference, and what we're going to call this function is get middle and split in half. I don't know if this is the best name, but it's pretty descriptive. Get the middle node. This function will return a reference to the middle node, and it's going to also cut the linked list physically, is going to perform a destructive operation on the list, which we're going to patch back together as we sew this list back. But what we're going to do is create that abstraction. And this is good in interviews. You want to abstract away your top level function so you have time to talk about the high level details. Don't get lost in the low level details. How is this going to be out of bounds? Is this going to give a +1 exception? We don't really know. Your interviewer themselves don't really know. They won't catch all of the off by ones. But what they will catch is the overarching concepts. Do you really know where you're going? Do you really understand where this solution is going, what you're doing? So yeah, abstraction is good. Initially, you're still going to implement it, but abstraction is good. Get, middle, and split in half. So what we're going to be yielded by that call is the middle point. So what we want to do is we want to recurse, sort the left half, sort the right half. So what represents what? The head represents the left half. The midpoint represents the midpoint onward because we split there. The head represents over here, and then the mid represents the rest of the list. In order to sort the left half, sort head. Sort starting from the head. So let's do that right now. What we see here is sort the left half, sort the right half. Left half, right half. This recursion is going to drill down until my base case knows. When my base case understands the answer, we're going to have resolved values here. When we have resolved values here, we can then operate on them. And what we return is we return the merged, sorted sublists. So that's what merge sort is about. Partition, continue partitioning until a single item, recurse, and then merge. And when we merge, we're eventually going to have a sorted array. So what we need to do is we say return, merge the left half and the right half. So right here, if you're in an interview and you needed to implement merge sort, this is your top level function. Notice we have established 3 abstractions, or 2 abstractions. We've established 2. We've established a merge routine, subroutine. We can implement the merge subroutine. We can implement the get, middle, and split in half subroutine. Do you see how here we don't even need to worry whether it's a linked list or not? We're just saying, I don't want to worry about this. I'll do this later. I know I have a midpoint. Operate on them by continuing to recurse, split, 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 and then merge. Once these guys resolve, when the base case comes back up, then we just merge. And this is the top level function. I'll post the full code in the video description so that you guys can investigate the actual subroutines, which are not that tricky to implement. You're going to eventually get familiar with it, but it's good to reference. So the more familiar you get with this, you become a lot less scared to implement this on the spot because you're going to deeply understand what you're really doing. Base case, recursive case, and sew things back together, which is what merge sort's all about. What we're going to look at is what does the time complexity pan out to be and what are we actually doing here? So let's draw a recurrence. What we need to do is evaluate the work that this overarching algorithm does, which we're going to represent the exact work as T of n. So here, T of n is going to equal 2 times T of n over 2, and I'll explain why. What we're doing is we're representing the recursive function as T of n. And we're going to feed the same function half of the original input every time. And we're going to go sort the left half, sort the right half. So the total work done at this level of recursion is going to be 2 times the work done on left half, the work done on right half. And ultimately, this is going to recurse. This is a recursive statement. We need to understand what is the actual work we're doing when we are at each of these levels of recursion. And that work is this. So if we see the length of this list as n, the length of the list at this level, if we cut the list in half and we sew the parts back together, at worst, we're going to compare every single pair of items until the last item, which we're just going to place into the sorted arrangement. Again, this is a super high level overview. There is complete full detail in my merge sort video. I just want to skim over this. When you solve this using something called the master's theorem or the tree method, you see that when this is solved, you reach an upper bound of n log n. And this is extremely apparent when you look at the actual derivation, which I have in the merge sort video, of the exact levels and the amount of work we do in each level. So there's roughly log n levels, upper bounded, and we're going to do about linear work at each level. That's just explanation in words, but it's a lot better to see the math. So again, the merge sort video is a great reference for that. So here is another example. If I have an array, let's draw an array of 5 items. N is 5. If I have this array of items and I decide to build a max heap, then one by one I'm going to be inserting these items into a structure that at maximum can be size n. And if the structure can be size n, that will indicate to us the maximum levels we can bubble down or bubble up an item after insertion. So let's build a max heap, you'll see what I mean, and really reference the heap sort video that gives an in-depth understanding of heaps, and I'll get a code implementation up of that as well, but let's do the example. So insert 3 into the heap. There's nothing, just insert 3. So insert 2 into the heap. This is a max heap, so insert the 2. Whenever we're inserting to a heap, insert as far left and as far down as possible. The 2 goes here, and we see, look at the parent. Is the parent less than me? Or is the parent greater than me? And then what we do is we put this item as far down as possible in the heap to keep it complete, to keep the binary tree complete. And what we want to do here is we want to see, parent, am I bigger than you? 2 is not bigger than 3. We still have a max heap. Everything's fine. So now insert the 7. And now 7 asks, hey parent, am I bigger than you? 7 is bigger than 3. So 7, swap with 3. So now 7 goes again, hey parent, am I bigger than you? But 7 has no parent. While loop ends. So this is still a max heap. The heap ordering property is still intact. So now insert 8. So now 8 says, hey parent, am I bigger than you? 8 is bigger than 2, swap. And then 8 says, hey parent, am I bigger than you? Swap 8 and 7. 8 is bigger than 7. And now our heap ordering property is still intact. Our parents are bigger than what is below them, their children. And 9, insert 9. So again, down as far left as possible, 9 goes there. And now 9 says, hey parent, 7, am I bigger? It is bigger, so swap. And then 9 says, hey parent, 8, am I bigger than you? Swap, 9 is bigger than 8. And so now great, we've built a max heap out of this array. And what we need to see here is, how many levels can an item ever go up or down? Well, it can only ever go up or down 2 levels. And this is a number we care about. This is the number that upper bounds. It gives us an upper bound. And how can we derive this number? If we think about it, how many nodes are in this level? 1. How many nodes are in that level? 2. How many nodes can possibly be in this level? 4. 1, 2. 2 missing nodes. 3, 4. So what we know is this level is 2 to the 0. This level is 2 to the 1. This level is 2 to the 4. So this is a complete binary tree. We're starting to express these levels as powers of 2. And powers of 2, that reminds us of logarithms. This is where logarithms come into play. And this is how we can bound, knowing the total number of nodes. If I take the logarithm of 1, 2, 3, 4, 5, 6, 7, that is going to give us the maximum amount of levels that we're going to bubble down in this heap. So 1, 2, 1, 2. This is where the logarithm comes in. If I have n items, that is a representation of how much work I can do in the worst case bubbling up or down. And if I have n items, then 1, 2, 3, 4, 5 operations, and at maximum bubbling down 2 levels, what's going to happen is parameterize the bound by n times log of the heap's levels. But that's n log n. So this is where n log n also comes into play. These are examples, and I just wanted to show you 2 examples of where we'll see big O and log n. So let's have a wrap up and review what we've learned. In conclusion, in this video, we learned where we can see manifestations of the big O and log n time complexity. We saw it in merge sort, how we have logarithmic levels, and we're going to do a certain amount of work per level. And in reality, we want to actually solve the math to understand that. If you're just in an interview, just know it's n log n. It's as simple as that. You won't probably have to actually do the math. If you can draw the recurrence, that's even more power to you. It's good to know. We also saw that if we have an array of n items and we build a max heap out of it, we're performing n insertions into a structure, the max heap, which will have a maximum n items, which means we can bubble up or down up to log n levels, which is big O of log n times, and that leads to the n log n as well. That's another appearance. This is a tricky time complexity, but if someone says sort this data in n log n, you almost immediately understand what is being asked. They want you to use a common sorting algorithm like merge sort, quick sort, and the like. So that is n log n, and what we're going to look at next is the time complexity of n squared, n cubed, that line of time complexities. That is what we have up next.